Good afternoon, sir.
Good afternoon, sir.
We'll wait for some time, sir.
Sir?
Now it's 12:55.
Sir.
1:05 will start, sir.
Done,
10
sir.
minutes.
Sure, sir. 1-5 we can.
So I can start, sir.
Yes, sir.
Students, don't on the videos.
Good afternoon, everyone. Welcome back to the online session for the physics CET classes. So today's topic of discussion, students. Today's topic of discussion, we have electromagnetic induction. EMI, we are going to discuss electromagnetic induction. So let us first discuss once, as always, we'll first go with a few concepts related to electromagnetic induction. Post that, we will take up a few questions and solve, okay? Fine, we have scheduled it for another day. All right, we will let you know when it is done, okay? Yeah. So students, I believe you are able to see the screen now. Let us start with the session for today. Electromagnetic induction. Students, electromagnetic induction is basically the idea of generating electric field in a varying magnetic field. So we have Faraday's law to begin with, where according to Faraday, there will be an EMF induced in a conductor or a coil until there is change in flux, or what we call it as magnetic flux linked with the coil. So until the magnetic flux is there, students, until there is change in magnetic flux, there will be an EMF. Also, Faraday's second law quantified this EMF. How much he quantified? Where he said that the EMF is directly proportional to rate of change of magnetic flux. EMF is directly proportional to rate of change of magnetic flux. Meaning, if I have a coil and let's say I move a bar magnet, then the magnetic field lines linked with the bar magnet is going to change with respect to coil. Whenever this change happens, students, there will be an EMF induced. If the change happens faster than the previous case, then the value of EMF will also be more. So this is what is our second Faraday's law. The third law, in fact, it's not called Faraday's law, it's called as Lenz law, which is also the consequence of conservation of energy, we say, where whatever mechanical energy that we are spending in moving this bar magnet or in changing the magnetic flux, that energy gets converted to electrical energy, students. And therefore, it is said that the EMF that is induced is equal to minus d phi by dt. So what is this negative sign here? This negative sign here indicates that the EMF will be induced always in a direction. Students, please write this down, which is most important. EMF will be induced always in a direction such that it opposes the cause which is producing it. Such that it opposes the cause producing it. So let me help you understand this much better with an example, students. Let's say that I have a uniform magnetic field. All right. Let's say I have a uniform magnetic field. Then, if I bring in a circle, all right, a circular conductor, if I bring it into the region, then we notice that the flux slowly keeps on increasing. Because of the magnetic field linked with the coil, the flux keeps on increasing. So as the flux keeps on increasing, students, we notice that there will be change in flux and EMF will be induced, but in what direction? Such that it is oppose the magnetic field. Students, in order to oppose this magnetic field, the coil will produce a counter magnetic field. That is, if existing magnetic field is going into the plane of the paper, which is a cross, then the magnetic field produced by the coil will be outside. It just counters it. It is opposite. Now, what do you mean by it counters or it is opposite, students? We'll have to make use of your Fleming's right hand thumb rule to understand the direction. Students, all of you, please do this. Take out your right hand in such a way that the thumb is pointing towards you, meaning dot. The thumb is pointing towards you. Then how are the fingers curling, students? In what directions are the fingers curling? It will be in clockwise direction if you notice. So that's when we say that when the coil is coming in, the magnetic field will be clockwise such that it opposes the magnetic flux linked with it. Likewise, if I take the same conductor and move it outside, see, this was when it is coming inside, it opposes the applied magnetic field. So when it is moving outside, students, we say flux will decrease. Second case, when it is moving outside, we say flux is decreasing. Now it has to oppose the decrease in flux. How will it oppose decreasing flux? By increasing it. Flux is decreasing, right? It has to oppose it. So what will it do to oppose? It should increase it. Increase meaning it will produce a magnetic field which supports the external magnetic field, and therefore in this case, the current will be flowing in clockwise direction. So therefore, students, when the flux was increasing, you notice that it was in anti-clockwise direction to reduce the magnetic field. When the flux was decreasing, it became clockwise to increase the magnetic flux. So basically, whatever happens, it will oppose the change. If it is increasing, the flux will try to decrease it. If the flux is decreasing, then the EMF will try to increase it. So this is the basic idea connecting Lenz law. This is our basic idea connecting our Lenz law. So students, please remember this in mind because it will help you in solving a lot of questions related to direction of EMF. Direction of EMF can be done. One more also I will tell you, students. Let's take another example. Let's say there is a magnetic field that is existing, all right? And we have a small conductor which is expandable. We have a small conductor that can expand. Students, if I expand the coil, then what is happening to area? Area is increasing. Because area is increasing, we say flux will also increase. Now, how should the EMF be produced, students? The EMF should be produced such that it should decrease the flux. And therefore, it becomes a dot. Meaning, current will be produced in anti-clockwise direction. Understood? So this way, if a coil is expanding, because of the increase in area, the flux will increase, but the magnetic field produced by it should decrease. That's why the current produced will be in anti-clockwise direction. And this is what is our Lenz law. So this is one other example. Now, having spoken about the laws, let us quantify a flux. We say flux is nothing but B dot A. Flux is nothing but B dot A, which expands as dA cos theta. Is that clear, students? Where what is theta here? Theta is the angle between magnetic field and area vector. Students, I want you to very carefully observe this. Let's say this is my area. All right, this is a rectangular coil, and some magnetic field lines are passing through this rectangular coil like this. There are some magnetic field lines passing through the rectangular coil. Students, can any of you tell me what is theta value here? What will be theta value? What will be angle between area and magnetic field? Students, here theta will be 0 degree. I'll explain how. Observe here. For area, we take normal as the direction of area. Is it clear to you, students? The direction of area will be always normal to the surface. Since magnetic field and normal are in same direction, theta becomes 0 or flux is maximum, we say. So students, if at all they give a question like this, the plane of the coil, all right, the plane of the coil makes an angle 60 degree, all right, makes an angle 60 degree
Please wait, he'll be coming back. Don't on the video. Student, don't on the video. We can start.
Am I audible to you, students?
Yes, sir.
Okay. Yeah. Thank you, sir. Yeah. Thank you, students. So I think I will continue. All right. So students, we were discussing the different magnetic flux linked with it. So I will, I was talking about the three ways in which you can change the magnetic flux. All right. There are three ways in which you can change the magnetic flux. One is by changing the magnetic field linked with it. Second is by changing the area. and third is by changing theta. So when magnetic field changes, we differentiate dV by dt. When area changes, it is dA by dt. Whereas when angle changes, it is d theta by dt. All right. So these are the three ways in which you can induce magnetic flux linked with the coil. So next, students, we will look at what is the idea behind your magnetic flux linked with a single coil. So students, if I take a single coil and I pass some current through this, then there is absolutely no effect on the magnetic flux. All right. But what happens if I change the current through the coil? Students, if I change the current through the coil, then the changing magnetic field will produce an EMF. And therefore, we say, because of the changing current, a back EMF will be induced. A back EMF will be induced. And this back EMF is produced by the coil itself because of the current passing through itself. All right. So that way, students, we notice that the self-inductance, all right, self-inductance, that is the opposition offered by the coil to flow of current through itself. Self-inductance is defined as L, and L is nothing but the self-inductance of the coil. Students, this self-inductance is basically the property of the coil to oppose any current passing through itself. Now, how do I quantify the self-inductance? We say that the flux passing through the coil is directly proportional to the back current, the current that is produced in the coil. The current that is produced in the coil, which means removing the proportionality sign, we get phi is equal to L into I. Here, L is the self-inductance. Students, this is self-inductance with one turn of the coil. For n turns, we say N into phi is equal to L into I. So this is the idea regarding our self-inductance, students. So if I differentiate this relation, then we get the back EMF produced by the self-inductance is minus L into di by dt. This is the back EMF induced in the coil. These are back EMFs. So whenever we have current changing in the coil, then we say there will be a back EMF. And that back EMF is such that it opposes the changing flux passing through the coil. All right. Likewise, we have mutual inductance, students. Mutual inductance is when you have current in the secondary coil because of changing magnetic flux in the first coil. So students, if I have two coils placed pretty close to each other and we change the magnetic or we change the current passing through the coil. If we change the current, then the magnetic field linked with the coil will also change. All right, magnetic field will also change. This magnetic field which passes through the second coil will produce a changing flux and hence a current will be induced in the secondary coil. So this is called as mutual inductance, where the change in flux due to primary coil will induce a current in the secondary coil. What does it mean? It means that phi is equal to M into I, where M is called as mutual inductance. Students, we write it like this. The flux passing through due to the first coil will produce a current in the second coil. The flux passing in the first coil will produce a current in the second coil. So this is how we express the idea of mutual inductance. All right. It is called as mutual inductance. So students, we have one very special case here. If I have two coils which are coaxial to each other, coaxial meaning one inside the other. If there are two coils which are coaxial to each other, then a change in current in the primary coil will produce a current in the secondary coil. And this is because of mutual inductance. All right. So please write down the relation for mutual inductance for two coaxial coils, students. Please write this down. In the case of two coaxial coils, self-inductance is given by M12 is equal to mu naught I1, no currents here, mu naught N1 N2 mu naught N1 N2 into pi R square into small l. This will be the mutual inductance. What is small n1, students? It is number of turns per unit length. All right, number of turns per unit length in primary coil. What is N2, students? It is number of turns per unit length in secondary coil. So one of you are asking, sir, what is the mutual inductance if both the coils are of different length? Students, if both the coils are of different length, then we take L of the secondary coil. We don't take L of the primary coil, we take L of the secondary coil. Is that clear? We take L of the secondary coil. All right, so this is our mutual inductance formula, students. Likewise, self-inductance is given by mu naught capital N square A by N, or mu naught small n square A into N. So this is for self-inductance. All right, and this is for mutual inductance. Is that clear to all of you? I hope you are all writing it down, students. The first one is for mutual inductance and second is one for self-inductance. So having said that, what is capital N is one of the questions by you. Capital N is number of turns and small n, students, is number of turns per unit length. Small n is number of turns per unit length. A is area of cross section. L is length of the coil. All right. So the next one is when we have two coils which are having self-inductance L1 and L2, then mutual inductance, students, between the coils is given by coupling constant or coefficient of coupling into root of L1, L2. If two coils are of self-inductance L1 and L2, then mutual inductance is given by the coupling coefficient into L1 into L2. Students, this coupling coefficient depends on geometry of the coils. All right. It depends on the geometry of the coils. Students, we have to do it based on the problem, actually speaking, where the coupling constants can be determined. Well, you don't have to really worry about a question as in coupling constants, but we can use this in the problem straight away. So when I discuss problems, I'm sure you will get a much more clarity on this. Okay. Fine. So this is to do with your coupling constant, students. Next is the potential energy. Students, we say that because there is magnetic field stored in the coil, we have the energy stored in the inductor as half Li square. Energy stored in the inductor is half Li square. I being the maximum current through the inductor. L is the self-inductance. All right. So these are the ideas related to your potential energy. Students, for entrance exam, additionally, we require a few more concepts. Let me tell you what else is required. Students, we know that flux d phi by dt can be written as d by dt of dA cos theta. Correct? Because flux is nothing but dA cos theta. Students, if I have to express current from here, see EMF is minus d by dt of dA cos theta, no doubt. Now, how do you find current from here? Let's use Ohm's law, where according to Ohm's law, students, we can write V is equal to I into R. Correct? Therefore, the current passing through or induced current becomes minus 1 by R into d by dt of dA cos theta. Or in very simple terms, we can say I is equal to minus d phi by dt, all right, into 1 by R. Is that clear to all of you students? So this is my induced current. Please write down. This is my induced current. Likewise, how to find induced charge? How to find induced charge? We know current can be written as dq by dt. Am I right? Rate of flow of current, students, is rate of flow of charge is current. So from here we get dq by dt is minus d phi by dt into 1 by R. Right, students? Where dt will get cancelled. Therefore, the charge induced Q will be equal to delta phi by R with a negative sign. This is induced charge. This is induced charge. So these are some additional concepts that are required for entrance students. Some of the additional concepts that are required for entrance. All right. So I think with that, I have covered all the grounds that are required for solving problems, students. With which, let me go to the questions. Let us quickly try out some questions, students. Let us quickly try out some questions. Let's start with the first question, students. All of you make a note of this. First question. See, we have a coil which is introduced between the poles of a electromagnet. So let us say, students, that there is an electromagnet, all right, north pole and south pole. There's a coil that is introduced between the poles of an electromagnet, such that the axis of the coil will be in the direction of magnetic field. The number of turns of this coil is small n. Area of cross section of this coil is capital A. When the coil is rotated by 180 degrees, when the coil is rotated through 180 degrees, the charge flowing through this is Q. Total resistance of the coil is R. Students, they're asking, what is the magnitude of magnetic induction? Students, do we know what is the meaning of magnetic induction? What is the meaning here, students? What are they asking? What are they asking here? Magnetic induction? Please understand, magnetic induction is another name for magnetic field. Is that clear to all of you? Magnetic induction is another name for what? Magnetic field. So having said that, students, let us get to the problem. So as we have seen in the synopsis before, current I will be 1 by R into delta phi by delta T, where I can be written as delta Q by delta T, correct? Rate of flow of charge is current, where time will get cancelled on both sides. Because time gets cancelled, students, charge Q can be written as change in flux divided by R. Students, change in flux is dA into cos theta 2 minus cos theta 1. Reason, it is angle that is changing from 0 to 180 degree. Observe here, initially it is in the direction of the magnetic field, meaning theta will be 0 degree. It is rotated to 180, meaning theta 2 will be 180 degrees. Is that clear, students? And there is a negative sign also outside. So we get minus BA cos 180. Can any of you tell what is cos 180? What is cos 180, students? You're right, it is minus 1. So we have minus BA into minus 1, minus 1. Minus 1 and minus 1 will give me minus 2. So we get 2 times of BA. Since there are n number of turns, students, since there are n number of turns, this entire thing I will also have to multiply with small n. Is that clear? I have to multiply with small n. So we get Q to be equal to n into BA, 2 times BA into n. And I think I missed out an R here, right? Missed out an R here. Simplifying this, we get Q to be equal to 2 times B into A into small n by R. Therefore, what is capital R, capital P, students? Magnetic field. That's what they're asking now. So magnetic field B becomes Q into R divided by 2 times small n into A. Students, that is there in option? Is there in option 4? Is that clear to all of you? I hope I'm clear to all of you, students. Good. Okay, once more you are telling me to repeat. This is how we represent current, induced current. From induced current, I wrote induced charge. From induced current, I used induced charge. Students, we know that induced charge is 1 by R into d phi, where flux is nothing but BA cos theta for 1 turn or NBA cos theta for n turns. Since theta is changing, I wrote change in cos theta, simplified and got the answer. Let's try the next question then, students. There are 2 coils, P and Q, and they are separated by a distance. When a current of 3 ampere flows through P, a magnetic flux due to P will be 10 to the power minus 3 Weber. That is when there is no current in Q. Next case, what they're telling. When there is no current in P, and the current passing through Q is 2 ampere, what will be the flux? What will be the flux? Did all of us understand the question? What will be the flux? Students, irrespective of what happens, geometry is not changing, correct? Distance is not changing, correct? Therefore, mutual inductance remains constant. Mutual inductance remains constant, which means that phi P will be equal to M PQ into I due to the current in P. Likewise, the magnetic flux due to Q students is MQP, all right, into current passing through Q. So having said this, students, the mutual inductance remains constant. You see that? Mutual inductance remains constant. And therefore, from this idea, we'll substitute when flux is 10 to the power minus 3 for P, when flux is 10 to the power minus 3 for P, all right, the mutual inductance, I'll take it as some M, which is constant. The current that is flowing is 3 ampere. When the flux through Q we don't know, the mutual inductance is still M, but current is 2. By taking ratio between these two students, 10 power minus 3 by flux through Q will be equal to 3 by 2. Therefore, what is flux through Q, students? 2 by 3 into 10 to the power minus 3. Which is the right option then? Which is the right option, students? Very good. Very good, Rashmika. Answer is option 1, students. Good, Surabhi. Good, students. Option 1 is the right answer. Very good, people. Let's try the next question. There is a coil that is suspended in a uniform magnetic field. So we have a coil and there is uniform magnetic field such that the plane of the coil is parallel to the magnetic field. So students, this is the plane and the magnetic field and the plane are parallel to each other. Magnetic field and plane are parallel to each other. When a current passes through the coil, it starts oscillating, meaning it will start rotating because of torque. Because of torque, it will start rotating. Question is, it is very difficult to stop, but it can be stopped by using an aluminum plate near it. By placing an aluminum plate near this, the oscillations can be stopped. Why can it be stopped is the question. Very clearly here, students, this aluminum plate is going to produce eddy currents. The aluminum plate is going to produce eddy current. What is eddy currents? They are the currents that opposes any change. Currents that opposes any change in magnetic flux by producing currents that are countering the change in flux. That is called as eddy current. So students, keeping that in mind, development of air current is wrong. Induction of charge in the plate, not really. Charge will not be induced. Shielding of magnetic field lines. Paramagnets never shield magnetic field lines. It is ferromagnets which shield magnetic field lines, students. Option 3 is also wrong. Therefore, as you all are telling, option 4 is the right one. And electromagnetic damping is because of eddy currents, students. Eddy currents. So Mohan is asking me to solve the previous question. Actually, the previous question is quite simple. The flux passing through the coil P is due to current in Q. All right, the current in Q. Likewise, the flux passing through Q will be due to current in P. I have just used that idea. Distance does not change. Geometry does not change. Therefore, mutual inductance between the two coils also remains constant. And I called this as some M. By taking ratio, I eliminated M. By taking ratio, I eliminated M. And simplifying, we got the answer. I hope it is clear now. Mohan? Yes. Yeah. Flux due to P they have asked. True. Flux in P is because of current due to Q. That was my idea. So flux due to P we can write this as flux due to Q is current due to P. All right. And flux due to P is due to current in Q. Yeah. Does that make sense now? I hope that makes sense now, students. Let's try the next one. I think it's a rather simple question. Self-inductance is given, students. Number of turns is given. Current is given to us. We need to find out flux. We need to find out flux. So we say N into phi is equal to L into I. Please use this formula and simplify, students. Vishwanath, I will explain the question after the class so that I am not stopping the flow of questions. I'll explain it after the class to you, okay? Just wait after the class for 5 minutes, I will explain. Students, answer? Option D, is it? Let us try it out quickly. 100 into 5 is equal to 0.05 into 0.02, which is 5 into 2 into, here I have 10 power minus 2. Here also I have 10 power minus 2. That makes it 10 power minus 4 divided by another 10 power minus 2. Sorry, 10 power plus 2. So flux 5 becomes 10 into 10 power minus 4 minus 2. Am I right? That makes it 10 power minus 5. 10 power minus 5. Next question, students. So this is a question connected to rod which is moving in the magnetic field. I think I had not discussed the concept with regard to this. So let me quickly discuss the concept here, students, before I get to the problem. Before I get to the problem, let me quickly discuss the concept also. So we say that in a uniform magnetic field, when we move a rod, in a uniform magnetic field, when we move a rod, then there will be a current produced in the rod, where EMF induced is given by BLV, students. EMF induced is given by BLV. All right. Where L is the length of the rod, V is the speed with which it is going, B is the magnetic field. Students, we must also understand vector form here. In vector form, we say EMF E is equal to L dot V cross B. It's called as triple product. It's called as triple product. So this is in vector form, students. L dot V cross B is in vector form, triple product. What does it mean is L, B and B are mutually perpendicular. L, V and B are mutually perpendicular. All right. L, V and B are mutually perpendicular to each other. Students, we see here that if the same case is taken where a rod is moving, let's say in this direction, will there be an EMF produced? In this case, there will be no EMF produced. What is the reason? Length and velocity vector are in same direction. Theta will be 0 degrees. All right. Length and velocity are in same direction. So what will happen here, students? If you look at velocity vector and magnetic field vector, these two vectors will be perpendicular to each other. Therefore, in this case, velocity vector and magnetic field vector are perpendicular. Therefore, theta will be 90, sin 90 will be 1. Now this is fine. But when you take the cross product of V and B, it will be perpendicular to the length vector. V cross B, students, V cross B will be perpendicular to length, which means B cross B, all right, will make an angle 90 degree with respect to length. Now we have dot product, which is L dot V cross B, correct? What happens here? If you look at dot product, there is L, V cross B, cos theta. And what is cos 90, students? 0. That's why you understand here that EMF will be 0. This is a very important idea, students. This is a very important idea where we can express this as scalar triple product. We can express it as scalar triple product. All right? Fine. Now, having spoken about rod, which is moving, we will also talk about the direction of the current. Students, in the case of a rod moving in a magnetic field, the direction of current is given by Fleming's right hand rule. Please write this down. Direction is given by Fleming's right hand rule. So what is Fleming's right hand rule? Let me quickly tell you, students. Extend the first 3 fingers of your right hand such that index finger indicates magnetic field. All right. Index finger indicates magnetic field and thumb indicates motion of the conductor. Then your middle finger will indicate direction of induced current. Middle finger will indicate direction of induced current. Is that clear to all of you? So if I apply that rule in this case here, students, let's all do this. Do all of you please do this with me. Point your index finger into the plane of the paper and point your thumb from left to right. Students, please repeat with me. Index finger into the plane of the paper, thumb is from left to right. How is the middle finger pointing? How is the middle finger pointing? Very good. Therefore, current will be upward. So this is our Fleming's right hand rule, all of you. Index finger magnetic field, thumb will indicate motion, and current will be indicated by middle finger. Now, having said this, students, this is at high potential. And this will be at low potential. Meaning, the upper part will induce a minus Q charge and lower part will induce a plus Q charge. So this is regarding the motional EMF we say. Likewise, students, if I take a rod which is rotating, this is from NCERT. Students. If I take a rod which is rotating in a uniform magnetic field, students, they ask plenty questions from this idea. Students, if they rotate a rod, then the EMF induced will be given by the formula E is equal to half B L square omega. What is L here? Length of the rod. B is magnetic field. Omega is the angular speed of the rod. So students, if I have many rods, but all are of same length, and it is rotating in uniform magnetic field, students, even in this case, even in this case, EMF induced will still remain E is equal to half B L square omega. What is the reason? The reason is all the rods will be in parallel. And in parallel combination, voltage remains constant. In parallel combination, voltage remains constant. Therefore, EMF will still remain the same. Which means if I take a infinite number of rods, if I take not 5 or 6, if I take infinite number of rods, then it will become a disk, no students? If I take infinite amount of rods, then it will become a disk, no students? Which means if I rotate a disk in a uniform magnetic field, if I rotate a disk in a uniform magnetic field, even in this case, EMF is half B R square omega, R being the radius of the disk. R being the radius of the disk. Is that clear? So one of you are asking, what happens if the rod is rotated through an angle, sir? If the rod is rotated through an angle, what is the formula? Is the question. Students, if rod is rotated through an angle, then EMF will be given by d phi by dt. d phi by dt. Where theta 1 will be the initial position, theta 2 will be the final position. So based on that, you can find out EMF. Is that clear, Bindushri? So this angle will be theta. We use that formula to find EMF when it is rotated through an angle. All right. So students, these ideas are important. With this idea, I think I will get to the problem now. Get to the problem here. So whenever I have a question like this in a circuit, students, what I immediately do, I write this rod to be producing an EMF of BLV, correct? Therefore, this rod can be replaced with a battery in the circuit. What can you do? This rod can be replaced with a battery in the circuit. Which means if I redraw the circuit, I'll get a battery. I will get two resistors. Correct? There is a shortcut, students. I'll get battery. I'll get two resistors. And the resistance of the connector is also given, meaning internal resistance. All right? So here, the connector will also have some resistance. And that is 2 ohm. Students, can one of you tell me how when 6 ohm and 3 ohm connected? Are they connected in series or are they connected in parallel? Students, please answer to my question. How are 6 ohm and 3 ohm connected? Are they connected in series or are they connected in parallel? Very good. They are all connected in parallel, which means 6 ohm parallel to 3 ohm will give me 6 into 3 by 6 plus 3, which is 18 by 9, 2 ohm. So students, I can rewrite this diagram as follows. 6 and 3 gave me 2 ohm. Another 2 ohm is internal resistance. And the rod produces an EMF, which is BLV. So students, let's find that value. EMF is BLV, 2 into magnetic field is 2, length is 1 meter, 1 into speed is 2 meters per second. So what is EMF, students? 4 volt. EMF is 4 volt. So students, I have a battery of EMF 4 volt. How are 2 ohm and 2 ohm connected? Are they in series or parallel? Students, how about 2 ohm? Are they in series or parallel? Series. Wonderful. Which means that the current produced current produced according to Ohm's law is V by R. In this case, it is E by R, which is 4 by 4, 1 ampere. Very clearly, the current passing through the rod is 1 ampere. Now the question is not current here. Question is, what is the force? Students, we all know force experienced by current carrying conductor placed in magnetic field is BIL. Yes or no? Yes or no? Force is equal to BIL. So students, magnetic field here is 2 Tesla. Current here is 1 ampere. Length is 1 meter. 2 into 1 into 1, how much we get? 2 Newton. So answer is, students, option 3. Students, answer is option 3. Are we clear with this? Are we clear with this or not? How did 2 ohm come? Maitri is asking, how did 2 ohm come? Because internal resistance is 2 ohm. Observe here. Internal resistance is 2 ohm. External resistance we solved. So totally 4 ohm. Is that clear to all of you? Good. Students, let's try the next question then. We'll try the next question. A coil is wound in the form of a transformer. A coil is wound in the form of a rectangular cross section. If the linear dimensions are increased, meaning length is also increased by 2 times, breadth is also increased by 2 times, and the number of turns per unit length remains same, what does the self-inductance change by? Students, formula, self-inductance is mu naught small n square A into L. Then mu naught small n square A into L. Now, having said that, students, if length increases by 2 times, breadth increases by 2 times, area will increase by 4 times. Area will increase by 4 times. Along with that, we also notice here that again there is a length dependence. Therefore, I have to again multiply by 2, which means 4 into 2, the total variation in L will be 8 times. Did you all understand, students? Did all of us understand? Others, are we clear? I got only one response. Others, are we clear? Good. Good, good. Please actively participate, students. Only then this program will help you. I think one of you asked me to explain the previous question. Previous question, I had done series parallel combination of the external resistors 2 ohm. Internal resistance is 2 ohm, they have already told. So that way I got the total resistance as 4 ohm. Total resistance capital R plus small r as 2 plus 2, 4 ohms. So from resistance 4 ohm and from EMF 4 volt, I got current as 1 ampere, force is BIL, and from there I got 2 Newton. I hope it is clear now. Friends, in that case, let us solve the next one. There is a metallic conductor of length L, 1 meter. It's vertical and it rotates about one of its ends with an angular speed of 5 radians per second. With an angular speed of 5 radians per second. If the horizontal component of Earth's magnetic field is 0.2 into 10 power minus 4 Tesla, what is the EMF developed? What is the EMF? Simple formula, students. EMF for a rod rotating is half B R square omega or L square omega. Students, please simplify this. Give me an answer. One of you say it's option D. Sudarshan, you are actually right. Others, can you confirm the same? Good. I got 4 responses. Others? Very good. That's nice. So we get half into 0.2 into 10 power minus 4 into 1 into 5. On simplifying, students, I get 5 into 0.1, which is 5 into 10 power minus 5, right? Or because there is no option here, I made it 50 into 10 power minus 6. Minus 6 meaning micro. Option 4. Option 4. Arfa, is it clear now? Samir, all of you, I hope you have got good. Good. One of you asked, why did they give horizontal? See, the rod is vertical. Then magnetic field should be perpendicular, right? Magnetic field should be perpendicular, right? Meaning horizontal. Is that clear now? Megha, I hope it is clear. Magnetic field and rod should be perpendicular. Therefore, if rod is in vertical, magnetic field should be in horizontal. Next question, students. A pair of coils of turns N1 and N2 are kept very close to each other. This is for N1, let me say, and this is for N2, let me say. The current through the first reduces at a rate of, so di by dt for the first one is R1, R actually, R they say, and the EMF induced across the other coil is 3 millivolt. Now, this is the first case. In the second case, if the current changes as 2R, then the EMF induced is what is the question? I hope you all understood the question, students. Now, because none of the geometries are changing, the mutual inductance remains constant. Students, we have formula E is equal to M into di by dt. So, EMF in the second coil is because of current in the first coil. Likewise, EMF in the first coil is because of current in the second coil. Students, please take ratio, give me an answer. Bindushri says option 3. Okay. Sudarshan says option 3. Mohan says option 4. Pavan option 3. 6 millivolt. Okay. Okay. Fine. Let us simplify, students. So E2 is equal to M into 2R. E1, I think they are given to us. 3 millivolt is equal to M into R. By taking ratio, M gets cancelled, R gets cancelled. So E2 by 3 millivolt will be equal to 2. Correct, students? Therefore, E2 becomes 6 millivolt. E2 becomes 6 millivolt. So one of you can ask me, sir, what happened to N1 and N2? Students, they get cancelled in mutual inductance. They get cancelled in mutual inductance because mutual inductance has that N1, N2 dependence. If you recall, the formula is like this, right? So that gets cancelled in this ratio. All right. Next question, students. There is a uniform magnetic field that is restricted to a region of radius small r in the first coil, the magnetic field changes with the rate of dB by dt. Students, can you write here at a constant rate? Students, please write here at a constant rate. Now, loop 1 has capital R greater than small r, whereas loop 2 has R but it is outside, which means there is no magnetic field in the second coil. So they are asking, what is the EMF generated? What is the EMF generated? Students, EMF generated is minus d by dt of B into A. Here theta will be 90, cos 90, sorry, theta will be 0, cos 0 will be 1. Theta will be 0, cos 0 will be 1. Therefore, we can say EMF is equal to minus d by dt of B into pi capital R square. Important here, students. Observe here, the flux is passing through the flux. Students, the flux is passing through the entire coil. Although magnetic field is restricted to a small area, the flux is passing through this entire coil. So whenever we say flux, we need to take flux of the entire coil and not only the region of magnetic field. So that way, students, in the first coil, the EMF E will be equal to minus dB by dt into pi capital R square. In the second coil, since there is no magnetic field produced, for the second coil, EMF will be 0, which means option 3 is the right answer. Option 3 is the right answer. Friends, please remember here, magnetic flux depends on area of the coil and not just area of the magnetic field. It depends on area of the coil. It depends on area of the coil. Let's try the next question, students. I think this is a simple one. I will give you a minute's time. Please give me an answer. I will give you 1 minute's time, students. You solve this and give me an answer. All right, I am getting some answers here, students. 0.2 out of which is majority of the answer. Let us quickly solve it. So I have to differentiate the students. Differentiation of 6t square minus 5t plus 1. If I differentiate 6t square, I get 12t. If I differentiate 5t, I get 5. The answer is 12t minus 5. But students, this is my EMF. If I put time as 0.25, EMF becomes 12 into 0.25 minus 5. Students, 0.25 is nothing but 1 by 4. All right. So I get 4 3s are 12. So 3 minus 5. And we also have a negative sign here, right? Because of Lenz law. That negative sign will get cancelled, students. So we get EMF to be 2 volt. Using Ohm's law, E is equal to I into R. So current will be E by R. So EMF we got 2 volt, resistance we got 10 ohm. Current is 0.2 ampere, students. Current is 0.2 ampere. Is it clear to all of you? Those who have made mistake, please correct for it. All those who have made mistakes, please correct it, students. Please correct the answer if you have made a mistake. Next question. It's a very commonly asked question, very important for entrance exam. A very commonly asked question in entrance. Students, we need to find voltage across AB, where we use Kirchhoff's voltage law to do this. We use Kirchhoff's voltage law to do this. So observe here that when I move from A to B, the loop will be from A to B. Current is also from A to B. Therefore, EMF, the voltage drop across this is minus I into R. Minus I into R. This is how we do it, students. All right, it will be minus I into R. But when I go for a battery, the current from the battery and loop are in same direction. And therefore, we take it as plus 15 volt. We take it as plus because for battery, same direction, meaning we take plus. Now coming to inductor, students, EMF across the inductor is minus L into di by dt. This is the formula. Minus L into di by dt. Where, observe here, they are telling decreasing at a rate. Decreasing at a rate, meaning di by dt, students, is minus 10 to the power 3. Decreasing, alva, minus 10 to the power 3. Then what is EMF, students? It is minus L. L is 5 millihenry. All right. Sorry, it is plus here. This is a plus here. All right. So L is 5 millihenry into rate of change of current is minus 10 into 10 power plus 3. So minus minus cancels. 10 power minus 3, 10 power plus 3 cancels. So EMF will be plus 5 volt. Students, EMF will be plus 5 volt. Mohan asked me, why negative sign? That is convention, Mohan. That is convention. Therefore, students, VA minus 5 into 1. Current is 5 ampere. Correct. Current is 5 ampere. Resistance is 1 ohm. Then plus 15. All right. Plus 5 is equal to VB. Which means VB minus VA will be plus 5 minus 5 cancels. I get 15 volt. All right, I get 15 volt. So answer is option 3. Is that clear to all of you? So according to Kirchhoff's law, when loop and current are in same direction, we take negative. when loop and current are in same direction for battery, we take positive. For inductor, we have calculated E is minus L di by dt, where current is decreasing meaning minus sign. So we get EMF as plus 5 volt. All right. So I hope you all understood the problem, students. Next one. This is again a commonly asked question in entrance. A commonly asked question in entrance. A jet plane has its wings of length 20 meter and it moves in west direction with a speed of 400 meters per second. If the Earth's total magnetic field is 4 into 10 power minus 4, such that the dip angle is 30 degrees, then what will be the EMF induced? Students, when the aeroplane is flying along horizontal, we have to take vertical component of magnetic field. We have to take vertical component. All right. So if BE is 4 into 10 power minus 4, horizontal component is 4 into 10 power minus 4 cos 30 degree. Vertical component will be 4 into 10 power minus 4 sin 30 degree. So students, this is what we need to take. So for an aeroplane, next time when we get questions, students, shortcut for an aeroplane, it is BV L into V, which is BE sin delta into L into V. This is a shortcut. So next time you don't have to think so much. If they are given Earth's magnetic field and dip, students, you simply take vertical component. So magnetic field is 4 into 10 power minus 4. Sin delta is 1 by 2. Length is 20. Speed is 400. On simplifying this, you get option 1. Students, you will get option 1. All right? Good. Let's try the next question, students. We need to find mutual inductance. Students, this will be the last question for today. So listen carefully here. By general formula, we say flux N5 is equal to M into I. This is a general formula. Students, if magnetic field is constant, then flux phi can be written as dA. But if magnetic field is variable, then flux phi will become A into dB by dt. Change of magnetic field. So why did I tell you this? Observe here that the distance from each part of the conductor keeps on changing, which means magnetic field at each point keeps on changing. So how do I solve the problem? Listen to this very carefully, students. If the current is I, then I am going to take a very small area of cross section in this part, a small area of cross section, and I am going to call this length as some dx. Then the breadth here will be equal to A because it is square of side A. So this will be the breadth, which means what is the area here, students? What will be the area here? Area will become dA, which is A into dx. Area will become dA, which is A into dx. Now let me say that the distance here from the conductor is some x. Students, by definition, magnetic field due to a straight conductor at a distance r from the center is mu naught I by 2 pi r, where instead of r here, I have x. So therefore, students, magnetic field at that point x can be written as V is equal to mu naught I by 2 pi x. Therefore, the mutual inductance, because there's just one term, flux will be equal to M into I, correct? Because there's just one term, or d phi, that is small flux passing through small area of cross section, will be equal to M into I, where d phi we can write it as d into dA. Meaning we are taking a small area and small flux. And what is dA? I told you, students, A into dx. So we get d into A into dx is equal to M into I. So from here, students, we can say mutual inductance M will be equal to B into A into dx divided by I. All right? Where this is again small mutual inductance. Magnetic field we have got as mu naught I by 2 pi x. Therefore, mutual inductance is mu naught I by 2 pi x A dx into I. So I gets cancelled. Integrating from one end to the other, I'll get the total magnetic induction. So I integrate here, students. What will be the limits? It will be upper limit, which is B. Lower limit will be B plus A. So B2, B plus A into mu naught A by 2 pi x dx. Students, we will take all constants outside. Mu naught by 2 pi A, mu naught A by 2 pi. We'll take it outside. What is left out, students? What is left out inside the integration? We have 1 by x dx. Students, integration of 1 by x. Can one of you tell me what is integration of 1 by x? Log x. Very good. Very good. Then we get mu naught A by 2 pi into log of upper limit B plus A, correct? Minus log of lower limit B. Students, on simplifying this, I'm sure you will get it as mu naught A by 2 pi into log of B plus A by B, because log A minus log B is what? Students, what is log A minus log B? It is log of A by B. So that formula is what I have used in this case. So by simplifying, I think we'll get option 3.
Time up, sir.
Yes, sir. I'm done. I hope all of you understood this, students. I hope all of you have understood this. With this question, I will wind up with today's session. Thank you. Thank you, students.